everybody, this is GL1, and if you are seeing this video right now, then I am missing, because the wizard in GL2 conspired to have me miniaturized and then taken by a scary clown. Fortunately, my friends came in a time machine camper and rescued me, and now no one knows where I am. However, before any of that happened, I made a video based on science, and that's no joke. So today, what I'm going to experiment with is volume, all right? So one of the things that I'm really curious about is how accurate are the Jurassic World, Jurassic Park dinosaurs, how accurate is their size in relation to the real thing, or what we assume is the size of the real dinosaurs, and comparing them as well to an African elephant. So how do you do this? All right, well, I have an African elephant model. Where did I put it? Oh, right. Okay, I have an African elephant model. Okay, he's dripping because I conducted the experiment. But this is an African elephant, and he is wrapped in saran wrap, and then I did my best to seal it with Gorilla Tape. And what I did is I have a pot of water that he will fit in completely, that you can submerge him. Now, how do you figure out the volume? So what you do is you fill the pot to a certain level, and then you mark where that level is, and I mark that with a piece of tape. Then I submerged the elephant, and while he was submerged, I marked where the water rose to. Okay, so the difference in where the water started and where the water rose up to is the volume of our toy elephant. Then what I'm going to do is I'm going to fill the water up to that mark, okay, where the final mark is, and then scoop it out and get it very accurately right to where the water began. And then I'm going to weigh that water. Now that will give me an idea of what that elephant it would weigh in water. Okay, so that's, let's say, going to be one elephant. All right. Then we have a certain weight of that, and actually the displacement in this pot was 3 centimeters. Okay. So what that means is the water rose 3 centimeters. That's his volume. All right. And we are going to compare that to dinosaurs. And I have 3 sauropods here that we're going to use. Now, the sauropods are so big that I had to get a big garbage can that I can submerge the dinosaurs in and lift it and put it on the scale. Because that's what we're going to do with the water here. We're going to scoop out that water, put it in another container, weigh the container before we do that so we can subtract that weight. Okay, so we're going to get a total weight of the container plus the water, and then we subtract the weight of the container by itself. That will give us the weight of just the water. We're going to have to do the same thing here. Now, the problem is getting a container, one, big enough to hold a sauropod model, Jurassic World and Jurassic Park, and be able to pick it up and put it on the scale and have the actual size of the container big enough to fit on the scale too. So, what the sauropods that I have are Apatosaurus. And as you can see, he's wrapped in saran wrap, and then all the feet and tail and head and everything are sealed with Gorilla Tape, trying to keep out as much water as possible, because I really want to keep all of it out. Because if the water gets into the dinosaur, into the joints, and starts to fill up, that'll throw off our measurement. It actually will reduce the volume that the dinosaur takes up in the container. And so we have to seal it. And because the dinosaur is so large, we're actually not going to be able to put the entire dinosaur in. So if you see here, the whole dinosaur doesn't fit. So what is our solution for that? So we're going to fill the water up to a particular level, and then we're going to submerge the dinosaur in halfway. We're going to mark with a piece of tape, okay, where that water level rose to, where it is on the dinosaur, and then we're going to also mark the difference, the change, just like we did with the elephant, the change in where the water started and where the water ended. And we will take that measurement, okay, so maybe it'll be like 2, 3, 4, 5 centimeters, and then we're going to flip the dinosaur around, okay, and then we will do the other side, stopping, right where the tape was, again, so that we just get the other half. And then we will take that measurement of how the water rose, and that will be the other displacement, and then we will add the two together, and that will give us the total displacement for Apatosaurus, the Apatosaurus model. And that will give us a weight. We will weigh that water, and we will compare it to the elephant. Now, you can go on Wikipedia and look up how much they estimate an Apatosaurus would weigh and how much an African elephant would weigh, and see if they're compatible. And then you can extrapolate, okay, then you can take that measurement of water, and what you do is we're going to take the length of this model, and we're going to extend it to the approximation of what they think an Apatosaurus, how long it can be, and see how heavy it can be, and then compare that water weight, our water weight, to the weight of what they say the real Apatosaurus would weigh to scale, okay? And I'll explain that more when I get there. So we're going to do Apatosaurus, and we're going to do Dreadnaughtus. Now Dreadnaughtus is huge. It's 5 feet long. So this really is the one that necessitated a really big garbage can. So I can only get that much of the Dreadnaughtus in there. So that's why I had to actually borrow this garbage can for this. And we're going to do our buddy from Jurassic Park, Brachiosaurus, okay? And then we'll do Brachiosaurus. So those we're going to do, and this I wanted to show you because I couldn't find it for the other Godzilla videos, but this is a cup holder from the 1998 Godzilla movie with Matthew Broderick. And the way this works is you roll down your window, and then you hook this in where the window depression is, and it's next to you, and then you have your drink there, or if you're a passenger, it would be here. And I believe this was from 7-Eleven for the Big Gulp, because it's Big Gulp size, and I think that's where I got that. But anyway, I will be getting back to you with results from our water volume experiment. Now, I'm done with the experiment, and I think some of the results are kind of surprising. But I want to once again explain to you how this was done. So, the elephant and all of my sauropods here were wrapped in plastic. In fact, they were wrapped in so much plastic so tightly that it took about 20 minutes to cut all the plastic off. And this garbage can is all the plastic that was on them. Now, this garbage can was weighed separately, and it's 3 pounds, all right? So, to demonstrate how this experiment was done, and the reason I didn't show you is it had to be done in a shower, and it was really messy, and it's just a lot to it. So I didn't want to put you through that, but I'm going to explain. So this garbage can was filled with water up to a mark right here, okay? That was the beginning mark. That was always the beginning mark of how high the water was. And then the sauropods were dunked into the water, and actually the Brachiosaurus and the Apatosaurus nearly completely were able to be submerged. Part of the Brachiosaurus, actually the neck, I was able to flip it around and submerge that and get a little bit more water. The Apatosaurus was completely submerged. I mean, there's just a little bit of tail left, but it was negligible. This guy here, the Dreadnaughtus, it really did have to go in halfway and halfway, and in order to get the volume. So he was, dunked in like this, and then kind of squish the tail in there and get it down, and then flip him around, and what I would do is I'd mark how far it went in to the water so I knew I was getting halfway. And each time when a dinosaur went in, you see, the water level would raise from that bottom mark. So when you would put, Dreadnaughtus in, for example, this water level would raise from here up to a certain height. Then what I would do is I'd use this pot, and I would scoop out the water. I would mark where the Dreadnoughtus brought the water up, right? Then take the Dreadnoughtus out, or the portion of him. Then I would use the shower head to fill the water up to that point. Then I would scoop out that water back down to that beginning level and dump it into this garbage can, which weighs 3 pounds. So what would happen is, let's say like for the Apatosaurus, being that the entire dinosaur was essentially submerged, it raised the water level up to a certain height, took him out, then I would fill the water up to that point to where he elevated the water, his mass, his volume elevated the water, and I would scoop out the water till it started that beginning point and put it in this garbage can. Then I would take this garbage can and I would weigh it, and I'd subtract the 3 pounds. That would give me a weight in water of how much volume this took up, okay? So then we compared that. We did it for all the dinosaurs, and we did it in the same way in a smaller pot, because he's much smaller. The garbage can, it wouldn't even register whether he elevated the water. But on a pot, you would actually see when he's submerged that it would elevate the water. And then once again, you mark where he elevated it to, and then you fill the water up to that point, scoop it out, and weigh that water. And I know that he was watertight, just like the others, because if he wasn't, his electronics would have been ruined. So I did not take the batteries out. I wanted to be sure and take a chance that I was sealing everything really well. All right, so that's how the experiment was done. And I would weigh that remaining water, right? So here's, now, with the science of the real creatures, a real African male elephant, a real, the assumption for how heavy a Dreadnoughtus, a Brachiosaurus, and an Apatosaurus were, I would take the average. So if it said, it's between, 30,000 pounds and 60,000 pounds, you would add those two together and divide it by 2 and get an average. And that would be the average weight I would go with. And I did the same thing with the elephant. I got the average weight of an African male elephant. And, of course, there's variations either way. But, going by the assumption, because it's all we have as far as the dinosaurs are concerned. So here's what we came up with. So the African male elephant, okay, was 3.4 pounds of water. That's how much water he took up, all right, which is quite a bit, actually. I was surprised. And the average male African elephant is 9,000 pounds. And we did the same thing for Apatosaurus. The Apatosaurus toy, 14.4 pounds of water, average weight, 39,000 pounds. Average Brachiosaurus weight of the water for the toy, 20.2 pounds. And this is in line with, actually, what's interesting, it is in line with what the fact that a Brachiosaurus is supposed to be heavier than an Apatosaurus. So it was, 6 pounds heavier, so, almost half again is heavy. And 82,000 pounds, so double. It's not quite double, right? So 82,000 is more than double the weight of an Apatosaurus. 20.4, 14.4 would be 18.8, 28.8. We had 20.2. So what that tells us is, even though the Brachiosaurus did register heavier than the Apatosaurus, it's not to scale with the Apatosaurus. If it were double, if it came out to 28.8 pounds of water or more, let's say like it would really 30 pounds of water, because it's more than double the weight of an Apatosaurus for real. See, the Apatosaurus 39,000 pounds, 82,000 pounds, which is 3,000 pounds more than double. So this would have to be a proportion of probably 30 pounds of water, but at least it is more. And then Dreadnaughtus, 21.8 pounds of water. The Dreadnaughtus is assumed to have been 130,000 pounds. Okay, so when we compare that with the elephant, all right, just to say, this is not to scale either. I mean, the water displacement weight is very similar for Brachiosaurus and Dreadnaughtus, but the Dreadnaughtus, again, is once again, it's almost 50,000 pounds heavier, is what they assume, which is, a significant amount, and the water weight is only 1.6 pounds, so not very significant. So if we compare that to the elephant ratio, okay, so the elephant ratio, if we divide the toy weight in water, okay, if we do a ratio dividing the Apatosaurus weight, 14.4 by 3.4, gives us a ratio. That means that the Apatosaurus water weight is 4.2 times that of our elephant toy. Well, the actual weight, when you divide 39,000 by 9,000, is 4.3. So actually, the Apatosaurus, one could say the Apatosaurus toy is an accurate model in its scale to that African elephant toy. Pretty fascinating. We go to Brachiosaurus. The Brachiosaurus toy is 5.9 times heavier in water than the elephant, and but the actual weight of a Brachiosaurus is supposed to be 9 times greater than an African elephant. It's only 5.9, so it's 6. So it's missing like 35% of its weight is off. Okay, so it's not actually big enough. And we go to Dreadnaughtus, and it's even significantly more different. The water weight is only 6.4 times greater than the elephant, but the actual weight is supposed to be 14.4 times that of the elephant. So pretty interesting, to figure out what is to scale and what is not to scale as far as these toys are concerned. So that's how you can conduct a volume experiment with your toys, and we can do this with other dinosaurs as well. And we can use our elephant, now that we have its water weight is 3.4 pounds, we can compare that to other dinosaurs, T-Rex or Giganotosaurus, anything, right? And figure out how it is, whether it's to scale. So now in terms of the size, the apparent size, it's actually, it's not a bad representation as far as, their size, but it just, when it comes to the volume, it just really didn't pan out that way. And I think most importantly is that they're quite cute. Now, if you haven't seen this, this guy here, his neck bends in both directions and up and down. So he can graze, like he's grazing to eat, and then he can look up, and then he can look over, and he turns there and closes his mouth. And if he wants to move his legs, maybe somebody's bothering him and he kind of wants to, kick them away, he can do that. And his tail bends in the other directions, and this part of the tail is rubbery. And our Brachiosaur, which we saw, you may not have seen it, but first time I went to Dinosaur Island, it's Brachiosaurus, and his head turns like that, and his mouth moves. And Brachiosaurus, meaning armed lizard, because he's got those big front arms, you know. And then his head also goes up and down, and the tail shifts back and forth. And then we have Apatosaurus, which was once called Brontosaurus, and then they said, no, there's no Brontosaurus. And then they went back and they said, you know, actually the bones are different, so we're going to say there is a Brontosaurus and a Padosaurus. So here's Apatosaurus. This fella here has a head that can move in all directions, and he's got like a little flappy mouth, not as significant as the other guys with like a jaw. His head does move back and forth. It does not go up and down. And the tail goes back and forth. It's got a little swivel there. It's more of a hard plastic, not as rubbery. And he does have some motion in his legs as well. So that is our Apatosaurus. All right, so thank you. And if you want to use your toys for science, volume and other things, you know, hope that gives you a little bit of an inclination to figure out how you can do that, and I'll be doing it more in the future. So thanks for watching. Have a good night.